So in the first lecture we covered the units and dimension. We derived the units of a huge large number of the physical quantity, and we also did some of the problems of conversion from one unit to the other unit. But there are a lot of other kinds of problems you will see, and today we are going to cover all these things. I'm not sure if it's going to help you, so give your comments in the YouTube's comment section. Before I start, I had some mistake in my last lecture, and I think I derived the wrong dimensional formula for the voltage, so you should correct that. If you want, we can go through this, but I think it's a simple thing. You should have found it out. So let's start. We will cover the homogeneity principle. We already have covered the conversion of units, so I'm getting rid of this. And then one of the uses of the dimensional formula is check if the equations are correct or not. So you wrote an equation, and if you're not sure, some formula is here and there, so you check the equations. And then you can also find the expression of expression of a physical quantity and you can derive these equations. We will do the problems in this one. And in the last, we have one type of problem where we find the dimensions in terms of the other types of problems. So let's start with the homogeneity principle. The name looks a little difficult, but it's really a very simple thing. The homogeneity principle says simply that you need to add one type of quantity into the same type of quantity. So you can add only velocity into velocity. You cannot add a distance to velocity. It's a very simple thing. What I'm saying is that if I ask you 2 minutes plus 4 meters, it is how much? It's an absurd question. So you cannot add a time to the distance. So in the same way, you cannot add the velocity to a distance. You cannot add a pressure to force, so on and so forth. If the x and y quantities are added or x and y quantities are subtracted, they have the same dimensional formula. We should note that this does not apply to the division. A and B can be divided even if they have different dimensional formula. Let's move on quickly and do some problems, and it will automatically become very clear to you. So let's say we are expressing distance. I call it, let's S is equal to AT plus BT square plus maybe C. We need to find out the dimensional formula for A, B and C. The dimensional formula for S is L, and that should be equal to the dimensional formula of this whole quantity. Not that S is equal to the dimensional formula of A. That's something you need to keep in mind. Dimensional formula of A we need to find. It's not A is the acceleration. We need to find what is A. A is a small constant here. So we need to find the dimensional formula of A multiplied by T. And this is possible, so the dimensional formula of A will be dimensional formula L multiplied by T to the power minus 1. So that is the dimensional formula of A. In the exam, you will write something like dimensional formula of A or something like that. I am going fast, so I don't take you much of your time, and then you solve this question. Now, the dimensional formula of BT square should be the same as the dimensional formula F, which is distance L. So that implies the dimensional formula of B will go to LT to the power of minus 2. You can verify it. Substitute LT to the power minus 2 here, LT to the power minus 2 here, T to the power 2 and T to the power minus 2 cancels, and the dimensional formula of B is this whole thing becomes dimensional formula of S. And finally, dimensional formula of C will be equal to L, the same as the S. There may be some complex type of problem, and one of the problems that is often asked is this equation. PV is a variation of the chemistry formula. PV is equal to, you know, that nRT, and a variation of this formula is expressed as we do some corrections to P and V, and we write it as P plus A by V square, P plus A by V square into V minus B is equal to nRT, and we need to, where V is this volume V. That means the actual pressure is slightly more because of some volume of the gas, and then this volume is reduced by the volume of the gas particles occupying or something like that. Now we need to find out the dimensional formula of V. So the dimensional formula of V will be equal to the dimensional formula of volume. We can only subtract volume from volume, so the dimensional formula of V will be the same as the dimensional formula of V, and the dimensional formula of volume is length cube, length multiplied by length multiplied by length. So this is part number A. Now we need to find the dimensional formula of A will be equal to dimensional formula of P, pressure, divided by volume square, and pressure is force divided by per area multiplied by volume square. Force we can write it as mass into acceleration, L t to the power of -2. Area is L square and volume square is L cube square, so this is L to the power 6. So 2 plus 6 is 2 plus 6 8, it goes up, this L to the power -7 t to the power -2. So this is the kind of the way you will be solving these problems, addition and subtraction of the same physical quantity. They should have the same dimensional formula. So the homogeneity principle, you may have some problems because of the homogeneity principle. So the next part we will move on to the checking the equations, correctness of the equation or correctness of the formula. Let us say we are given a formula, high school formula, V square is equal to U square. Final velocity is given as initial velocity square plus 2ax, and we want to find the correctness of this formula. V is the velocity, so this has the dimensional formula s square. We need to check that all parts of this equation, and equation can be equated to the left side of the equation should be equal to the right hand of the side of the equation, and in an equation all additions terms should have the, or the subtraction terms should have the same dimensional formula. U is also velocity, so this will also have, velocity has the dimensional formula of Lt to the power of -1 whole square, and that should be, and this is also velocity, so Lt to the power of -1 to the power of whole square. So this terms obviously match. What we need to find out is this term becomes L square t to the power -2. What we are trying to find out is the dimensional formula of this thing is equal to the dimensional formula of 2ax. So the 2ax is nothing but acceleration. A is acceleration is Lt to the power of -2, and distance is L. So this has the dimensional formula of L square t to the power of -2. So left hand side, the dimensional formula of the left hand side is equal to the dimensional formula of the right hand side. So this equation is correct. Similarly, you can find if the x is equal to ut plus half at square. Another formula we have read about the distance traveled in time t by a particle moving in the initial velocity s equal to ut plus half at square, and a particle moving with an initial velocity u in time t covers the distance x given by this, where a is the acceleration. We need to find out the dimensional correctness of this formula. So x is the distance, so this one will be L. U is the velocity, so L t to the power -1, and t has the dimension of t. This multiplies, this becomes L. So L is as dimensional formula of x is L. Ut has dimensional formula of s. So this part and this part are good. Let's try this part. Half is a constant, so they have no dimensional formula. A is the acceleration, that will have the dimensional formula of Lt to the power -2, and t square has the dimension of t square. T square t to the power -2 cancels, has the dimensional formula of s. So this formula is dimensionally correct, although the dimensional formula does not predict the correctness of these constants half here. Next we have an NCERT question 2.15. Let's do this one. It says that from the theory of relativity, the mass is something is moving something close to the velocity of light has a mass that varies something like, and it says that the guy got the answer wrong as m naught divided by 1 minus v naught square to the power of 1 by 2. What v naught square by 2, and somewhere in the formula he is missing the velocity c, and we need to find out where does he is missing this c in somewhere in the formula. So we need to must each other. This is mass, left hand side is the mass m, so the right hand side should also be mass. On the top side we have mass, so this term, something on the bottom should be a dimensionless quantity. So when this is a dimensionless quantity, that means 1 minus v naught square should also be a dimensional quantity. This is the square root of whole thing, so this thing also will be dimensionless. Now 1 is a constant, and from 1 we are subtracting a velocity square. This is not true. The dimension of this thing should be equal to same as the dimension of this thing. We cannot do anything probably here because this is a dimensionless. So let's try to make sure that V naught square has the dimension of L square, and that should be equal to the constant. So the only way we can do is by dividing it by c square, which is the velocity of light. If we divide this term by c naught square, then this thing will have the dimensionless character, and so the possibly the correct formula is m naught divided by square root of 1 minus v naught by c naught whole square. So that is another way we check the correctness of the formula, whether the formula is correct or not. The next thing we will cover is we will try to derive some formula. Derive the formula. Let's do some questions. Let's take a look at this example, and that is how we will find an equation. Finding an equations. We are here we did the checking the equation, and we in the next portion will be find an equation. Let's say Einstein says energy that we can find from a mass, it depends upon the mass and the velocity, and we do not know what that power will be. It depends upon a to the power b, m to the power, let's call it x, and c to the power of y. We need to find out the value of x and y. If we can do that, we can also derive the Einstein's formula using the dimensional analysis. Now energy is nothing but the work done, and the work done is force into distance. The force is ml to the power ml t to the power of minus 2, mass into acceleration, and d is length, so multiplied by length, this becomes ml square t to the power of minus 2. So left hand side is done. Now the right hand side is mass to the power x, and c is the velocity of light, which is again a velocity of this velocity, whether it's for light or something else, and we express it as ml t to the power minus 2 to the power of y. And we can write it as m to the power of x, l to the power of y, t to the power of minus y. Now let us equate these two equations. X, m to the power is 1 here, x to the power 1 is here, so 1 is equal to x. We found the x. Now we need to find out y. So we have l square, so 2 is here, and l is to the power of y here, so y is equal to 2. We can verify if this is good or not by using a third equation. T to the power minus 2 here is equal to t to the power minus y here. So this also gives y is equal to 2. So we verify that this formula is going to be m to the power 1 and c to the power 2, and this is the famous E is equal to mc square derived from the dimensional analysis. Let's take a look at another problem in which a body falling under the gravity has a velocity, final velocity given by g, which is the acceleration to the gravity, to the power q, and h to the power of q. H to the power of q. We need to find out what will be the values of p and q. The velocity has a dimensional formula L, t to the power of minus 1, and acceleration due to the gravity has a dimensional formula of L t to the power minus 2 to the power of p multiplied by height has the dimensional formula of L to the power of q. Now L to the power 1 is 1 here, and what is the L to the power here? L to the power p, so we write p here, and here L to the power is q, so p plus q. And secondly, t to the power minus 1 here is equal to t to the power minus 2p here, and then plus q here. We need to solve this equation. Let us subtract from this equation, so p LT meter per second square t to the power. So 1 L is equal to 1 here, and I think something is wrong here. So t to the power of minus 2p, there is no t here, so minus 2p is equal to q. This means p is equal to 1 by 2, and let us substitute p to the value here. We get q is equal to 1 by 2. So the final formula is g to the power 1 by 2 or h to the power 1 by 2, and we can also write it as square root of pq. So this is the velocity formula in terms of g and h. We can move on. We will do a couple of more problems because this is the most common problem is asked in the exams. And let's take an SC Verma problem where K is represented as, K is the energy represented as small k, moment of inertia I to the power A and omega to the power of B. I'm not sure if the K is something, let us say K is energy here. And then we need to find out A and B, where I is given as the moment of inertia is 2 by 5 mr square. They can also ask about energy, they can also ask about K as something else, for example rotational momentum or something like that, angular momentum. So I'm assuming that K is energy, that there will be different formula of I and omega. So if it is energy, then energy means force into distance. So force multiplied by distance, force is m L t to the power minus 2, distance is L, is equal to K is constant, we don't worry about it. I is m L square to the power of A multiplied by omega is angular momentum, and angular momentum is delta theta divided by delta t. Delta theta is dimensionless, we have covered it in the previous topic. Delta theta is dimensionless, this will be t to the power of minus 1 whole to the power of B. And if we try to solve this, m to the power is 1 here and m to the power is 2 here, and 2 into m to the power of A is here. So we got A is fixed at, we found the A here. Now the next thing is L into L is L square, so 2 here, and on this plane we have 2 into A. This implies, this also gives A is equal to 1. So this is not giving any other solution. So let's try t to the power is minus 2 here, and here t to the power is minus 1 into B. Also, so this is equal to minus V. This implies B is equal to 2. So let's substitute A equal to 1 here, B equal to 1 here. So we have energy K is equal to I omega square. This is the rotational energy of a moving particle, similar to the mv square. Kinetic energy half mv square. In, of course, we had the K here, we dropped the K here because that is the constant. From the dimensional analysis, it does not matter. Let's do another problem from the electrical engineering field. We are given that the energy in a resistor, this is a resistor, and there is a current flowing into it I, and this energy depends upon I to the power A, R to the power B, and time t to the power of C, to I R t to the power C. So this is the energy in time t consumed in this resistor. We need to find out dimensional of A, B and C. So we need the energy is work done, force into distance, and force is nothing but mass into acceleration, ml t to the power minus 2, and multiplied by d is ml square. On the right hand side is a little complicated, but let's try to find out. I is, we can find time is t, this is simple. Now the resistance R we can find from I has the dimensional formula of I to the power of A, because current is a fundamental unit, so we write it I to the power A. To find out R, we use the Ohm's law, V by I, and voltage can be expressed as work done on a unit charge multiplied by 1 upon I, and the work done is force into distance, and then Q is I into T multiplied by I. Now energy is force into distance, and this force into distance we can just simply write force into distance, force into, okay, let's write everything. And now the force is m L t to the power of minus 2, mass into acceleration multiplied by distance L divided by I square into T. And now this whole thing, whole thing goes up, m L into L is L square, t to the power minus 2 divided by t cancels, so the t to the power of minus 3 here, and then I square divided by I square to the power whole to the power b multiplied by this time t. Now let's equate the whole equation. M to the power is 1 here, so 1 equal to m to the power b here. So b is equal to 1, that is fixed. When b is equal to 1, this whole thing gets simplified, this t to the power of c here. The next thing we're going to do is L to the power 2. 2 here, and what is L here? You have L to the power 2b here, it is 2b, and then this also gives the same thing, b is equal to 1, nothing new. The next thing we'll do is t to the power of minus 1. So t to the power of minus 2 here is equal to this is t to the power of minus 3b and plus c. This implies b is equal to 1, so minus 3 goes here, 3 minus 2, this implies c is equal to 1. So we have c, value of c is here, b is here, a is left. And a we can get by comparing the dimensional formula of I. On the left hand side, I to the power is 0, and on the right hand side we have I to the power is a, and then here I to the power minus 2b plus 0 is equal to 0. And we have b is equal to 1. If you substitute b is equal to 1, a will be equal to 2. Minus 2 goes over here, so a is equal to 2. And if you substitute this formula, we get energy in the resistor as I to the power 2 or I square, R to the power 1 and T time. So this is the formula for the energy in a resistor. This is how you can derive the different formula for if you know the dimensions of the things, you should be able to, if you are confused in the exam, for example, if something is right or not, you can just on the spot do a quick check of what is this formulas are. We can also check the, let us say the energy in a capacitor is given by C to the power A and V to the power of V, and this is a capacitor and the energy is stored in this capacitor. Okay, I will leave this problem because we have not gone through the electricity, so there will be too much of derivation, but once you have gone through this, we can go through the problems like this. One last type of problems that I have here is one type of problem they ask is the fundamental units. If the fundamental units are mass, length and time, instead of mass, length and time, what if you expressed it into some other types of the fundamental units? And one of the questions we have is, let's say velocity and time and force. These are the three given quantities. These are the three fundamental quantities: velocity, time and force. If these are the fundamental quantities, we need to find and we need to express mass in terms of these three fundamental quantities. What will be the dimensions of V, T and F? We are given, let's say mass is expressed in terms of the velocity to the power A, time to the power B and force to the power of C. We need to find out A, B and C. So here what we'll do is velocity we express Lt to the power of minus 1 to the power of A. Time is T to the power B and force is mass into acceleration. So M L T to the power minus 2 to the whole to the power of C. Let us say this M, now equate the powers of these particles. So M to the power 1 is 1 here. We have 1 here, and then give me a second. Okay, I think I'm okay. So there is some reflections here coming up, but it's temporary. I'm about to end, so I don't care about it. Now mass here is M to the power C here, so this will become 1 is equal to C. And then let's equate the dimensions of length is 0 here. On the right hand side, L to the power is A here, and where else we have C, L here. So L, A plus C is equal to 0. This implies A is equal to minus 1. One more quantity we need to find is of C. A, C, we need to find B. So for that we will have the power of the time. It is 0 here, and power of the time is minus A here, and then plus b, and then minus 2c. C is 1, C is 1, so it becomes minus 2 here, plus b here, a is minus 1, minus into minus 1 is plus 1, this is equal to 0. This implies b is equal to 1 minus 2 is minus 1 goes this side, b is equal to 1. If we substitute this thing, we can express mass as velocity to the power of minus 1, time to the power of 1, v minus to the power of minus 1, to the power 1, and c to the power of 1, v minus 1, t and c. So this is another question. I hope this is enough for this. There are many more problems that you need to solve at the end of this your book in SC Verma or any other book that you are working on. Try to solve all the problems. If you have any questions or if you don't know the answer of anything, you can put on. In the next lecture, maybe I will either take the NEET and IIT questions in dimensional formula, but I thought that there is another section of the accuracy of the results and the significant figures, so on and so forth. So we may have one more lecture for that as well.